Hi there, this is about rethinking fractional quantum Hall anions via algebraic topology of exotic flux quantization. Here's the motivation. So fractional quantum Hall systems, I'll say FQH for that, are known to feature anions, as opposed to some other systems that gain a lot of press these days. So this goes back to 2020, work by Nakamura, but has been confirmed by a whole series of groups since then. So this seems to be a quite robust experimental result. Here's Nature advertising this result in 2020. Welcome anions. So these are fractional quantum Hall anions. And hence, therefore, fractional quantum Hall systems serve as potential hardware for topological quantum systems. That is, if external control of these anions can be achieved, a point that is not always highlighted that much. But the actual idea, the original and still valid idea of how to actually topologically protect the quantum gate using anions is that you get control of these anions, you pin them down, and then move them around. The cartoon here sketches how this is supposed to look. So you move these anions around by braiding their world lines, and that by the adiabatic theorem, if you do it slowly enough, enacts a unitary operator on your digital ground state of the system. And that unitary is the topologically protected gate. Now, despite successful FQH model building, very successful over the last 30 years, involving trial wave functions, Laughlin-Moore-Reed wave functions, composite particle lore, and effective Chern-Simons field matching, the theory of FQH anions actually has remained a mystery. I mean, this is not only highlighted that much, but it's an open secret. One author who very vocally amplifies this point is Ananda Jain, and in his two books he has sections that are actually titled The Mystery of FQH model building. It's just that there is no theory actually available, or was no theory available how to go into the non-perturbable regime and actually understand why that system would rearrange itself to form specifically the kind of anions that one observes. But to get a handle on this, let's observe that FQH topology is actually carried by the surplus magnetic flux quanta, also known as the quasi-holes or particles or the vortices of the system. So here's the cartoon picture that people have in mind, even though, as I said, there is no real deep explanation of this, but this seems to be correct on some level. It's just borne out by experimental observation. So it's unit fraction 1 over k, often called 1 over q. I call it 1 over capital K here for reasons that maybe I'll get into later. In such systems, a single electron is thought to be somehow paired or coupled or bound to, in some way or other, a k flux quanta. So there's one electron per k flux quanta, and at the exact filling fraction 1 over k, these are all exactly absorbed. But then every additional flux quantum that is brought into the system by tuning up the magnetic field just a little bit, it has to be unpaired, because by assumption everything else was already paired at exact filling fraction. So every such additional flux quantum acts like the defect, the missing of 1/k of an electron, and therefore it's called a quasi-hole. And it's these quasi-holes, these flux quanta, and or the vortices they induce in the underlying electron gas, which will play no further role in my discussion here. These will be the actual anions of the system. So this suggests that fractional quantum Hall effect actually rests on a form of exotic flux quantization. So it's these flux quanta, or their exotic new nature in these systems, that actually carries the quantum topology. So here's a cartoon highlighting that if we're talking about braiding anions in these systems that become braiding phases, topological phases. It's ultimately the flux quanta that braid around each other. And of course, with them, the vortices in the corresponding electron gas, the 2D electron gas. But for most, it's the flux quanta. But just that magnetic flux quantization actually appears to be inconsistent in the effective Chern-Simons description that has been used for many years now. This is not hard to see. It's rarely highlighted, though. It has been highlighted in lecture notes by Edward Witten in 2016 and David Tong, who both point out that there's this problem. They wave their hands a bit about how to just proceed with it anyway. But just on face value, Chern-Simons theory is not actually compatible with the standard Dirac flux quantization. It comes down to the fact that the equations of motions in this system just says that the electron current, which in this effective Chern-Simons theory is actually the flux density of this auxiliary gauge field, and hence must be integral, because it's also there an integral number of electrons, is actually, if we're in unit fraction Q, so now I call it Q anyway, that was the capital K before, so actually the Qth fraction of the total magnetic flux minus the quasi-particle density. But on the right hand side, the F and J quasi, these are integers, F by ordinary Dirac quantization. So that this is actually incompatible, this equation. It says that one integer is 1 over Q of another integer. So this is not actually compatible with the introvert flux quantization. And that means that some of the very foundation of Chern-Simons theory, of the standard effective long-range infrared theory of the fractional quantum Hall effect, rests on a, how should one say, on a paradox. It doesn't properly describe the system actually. So our approach is different. We proceed in 3 steps. The first is to find the mathematics of actual exotic flux quantization. Turn the situation right side up. Instead of starting with something that is incompatible with the very nature of the system, let's first of all get a handle on what that proper nature should be, mathematically. So this is something we've been doing in the last years. First summarized in this book, The Character Map in Non-Abelian Cohomology. I'll come later to why it's called the character map, but this is really about flux quantization. And then a more physics-oriented summary was published in the Encyclopedia of Mathematical Physics called flux quantization. The second step then is, once we have the general rules for flux quantization in hand, is to hypothesize a quantization law for the FQH flux. This is the analog of postulating a Lagrangian density. It's the physics modeling step. Once you know the rules of the general physics that you want to employ, you have to pick the laws of physics that you want to use. And so this means here to hypothesize a flux quantization law that describes magnetic flux in the exotic situation of FKH systems. And then, alright, so this is, so the flux quantization law we're going to use is the one we kind of derive from some brain physics in this article here. So many of the things that I'm going to say here, all of the things actually, we originally derived and arrived at from geometric engineering of quantum field theories on M5 brains after flux quantizing these brains. But you need not, and must not maybe, pay much attention to this background story of high energy physics here, because it's a fully self-contained story, independently of how we arrived at this. I'll present a new history, a new story, a new theory of just fractional quantum Hall systems that's just self-contained in itself. And then once we've hypothesized the quantization law this way, so then we have our physical theory set up, well, then we should derive its predictions to see what it implies. And the way this is set up, turns out these predictions are all derived just by applying algebraic topology, tools of algebraic topology, in a rigorous way to just analyze what's going on. And these results are those of an article we're finalizing. This should have been on the archive the other week already. It'll take us another week now to finalize it. There was some delays due to travels and stuff. This is this article of a similar title as these lectures. Here is this talk, Rethinking Fractional Quantum Hall Anions by the algebraic topology of exotic flux. You can find the link in the description. So the result then we get from this is that, first of all, actually we recover the standard hallmarks of the fractional quantum Hall system as it should be. The fractional statistics, the abelian fractional statistics, the topological order on tori, the edge mode phenomena. Up to some subtle details to this, actually we find some discrepancies, for instance, for non-unit filling fractions. For some of them, we actually get different ground state degeneracy than is predicted by K-matrix Chern-Simons theory. And I'll sketch arguments for why there's good reason to believe that actually the result we give must be the correct one, and the other one cannot be correct just on symmetry grounds, actually, just on modularity grounds. It seems like some of the predictions of K-matrix Chern-Simons theory, which is all a local theory, and not usually discussed, even modular invariance is not usually discussed for it. And I think for some of the non-unit filling frictions it actually breaks your modular invariance, which means it's inconsistent as a topological field theory really on tori. And this is actually fixed in our approach. But anyway, so broadly it actually matches fractional quantum Hall systems, certainly at the unit filling fractions and so forth. And so one way to look at it is it's a new theory which is makes slightly different predictions. So it's experimentally discernible. You could go if you ever manage to actually measure ground state degeneracy for FQH system on the torus, then our theory would be experimentally discernible from the standard Chern-Simons effective field theory. But moreover, actually, our theory should predict something more. You can just keep running with it on different kinds of surfaces, namely surfaces with punctures, which I'll explain corresponds to equipping our 2D electron gas with superconducting islands. And it actually predicts that at these punctures, these superconducting islands, there appear defect anions, in contrast to the solitonic anions that are zipping around in the system in our abelian. There are these localized pinned defect anions wherever flux is expelled, as one expects to be in superconducting contaminated regions. And these defect anions are potentially non-abelian and controllable. But potentially means, so the theory, I'll explain this in a moment, the theory tells you which irreps are admissible for the anions to transform into, and this will include non-abelian representations of the braid group. Whether these are actually realized in experiment, the theory can't really say. It does not say at this point. It just says sort of, if you have this exotic quantized flux that we will show we do have in fractional quantum Hall systems, then the non-abelian defect anions are a physical possibility. There's another question is which systems will realize it, but it will be worth looking for it. And this will be a big deal, of course, or would be. So here's a cartoon of these defects. So these little ellipses are my generic picture, as you will see, for these flux expelling defects. And so it predicts that you could be able to braid them around to enact non-abelian braid representations on the degenerate ground state. Okay, so let's start by recapping some of the standard lore and then proceed to less standard lore of magnetic flux. So let's go all the way back, 1851. Faraday makes his famous experiments and sees that magnetic fields come in with these flux lines that he first visualized famously by string iron filings over rod magnets. So the modern way to phrase this is to define a differential 2 form, F2 here, which measures the density of flux lines through any piece of surface that you have. So you integrate the 2 form over a surface, and you get a number that is the integrated number in some normalized units, sort of flux lines that pass through that surface. And in this way, there's this 2 form is the measurement, the incarnation of the flux lines of the magnetic field. F2, Faraday tensor. It consists of the electric and the magnetic flux. So since our system is just sitting there, it'll just be magnetic flux. So then we call the ordinary magnetic flux quantization. So it turns out that just this 2 form that we just discussed is not actually the full description of the electric field. It was thought to be so by Maxwell, and ever since 1850, ever since Maxwell formulated his theory, until 1931, Dirac formulated what is now called Dirac charge quantization, which in particular says that no, the electromagnetic field is actually richer than this. The gauge potential plays a role, but there's also global consistency conditions on the gauge potential, making it what sometimes is called a connection on a circle bundle. And these global conditions actually force the flux, the total flux, to come in quanta, to be quantized in the sense of to be discretized in the kind of old sense of quantization. But we'll see it's actually tightly connected to the actual quantization of the flux. Anyway, so this standard Dirac, 100 years old now, flux quantization is standard. Here's not many texts though really discuss it very well. One that does is this article by Alvarez, Orlando Alvarez here, Topological Quantization of Quantum Cohomology, who very clearly explains how to understand electromagnetic flux quantization and Czech cohomology. And then of course in our review article about flux quantization, which includes the exotic part, we also review the standard case. Anyway, so what does it predict? Well, I'll give you the formulation that is not always, or probably never in physics book highlighted, but which is the classical way of doing it in math actually, and that is the way that we generalize. So just bear with me here. This is the way to go. If you haven't seen this before, it's time that you see it. If you've seen it, it's just a standard story actually. For a moment, we'll generalize in a moment. Anyway, so the flux quantization is encoded by what is called a classifying space, an abstract space, not a physical space, but a topological abstract space, which goes by a lot of names. One is BU1, which is just math jargon for classifying space of the U1 gauge field. A model for this, as the mathematicians would say, is CP infinity, the union of all the complex projective spaces that all sit inside each other as n ranges, as the dimension n ranges. So you kind of glue them all together, take the infinite dimensional complex projective space. Another name that I didn't put on the slides here is, this is an Eilenberg-MacLane space called KZ2. Whatever, these are just terminologies. And the characteristic property of this classifying space is the following. This is essentially the definition. I'm omitting some fine print here, where essentially the point is that these spaces classify ordinary cohomology. So BU, KZNs classify degree n integral cohomology, and our KZ2 here, BU1, classifies integral cohomology in degree 2, which means that as we form the space of all maps from our spacetime X into this CP infinity, the space of all maps, so the space whose points are maps, it carries itself a canonical topology called the compact open topology, forms such a topological space, and therefore therefore we may take the connected components of that topological space, which is the topological content in the flux. The connected components means we identify, passing to connected components, pi 0 here, means to identify two such maps if they're homotopic to each other, if they can be continuously deformed into each other. So it identifies kind of these maps if they're topologically the same in some sense. I guess I'm using, so you should be aware that the physics use of topological is really what in math is called homotopy classes or homotopy. Anyway, so that's the almost defining property of CP infinity, that it classifies integral cohomology. And of course, it's no coincidence that we're talking about integral cohomology in degree 2 here, because we just previously saw we're dealing with a differential 2 form. And we'll see in a moment, we want to be identifying this differential 2 form as far as it goes with within class and integral cohomology. So then the statement is actually that the global electromagnetic field is not just the flux density F2, consisting of the electric E and magnetic B flux, but it also involves, like specifying the global field also involves in a formulation that is known as the homotopy pullback construction of generalized differential cohomology in math, and which in physics is actually not known maybe, or not widely known, but anyway it's a fact that in addition to that 2 form, the full specification of the field actually involves one such map from space-time to CP infinity. And then on top of that, it involves specifying the gauge potential globally, which in this formulation actually is itself a homotopy in a suitable topos theoretic world between the first 2 data points. But I'm not actually going to go into this. All we need is, so this is the proper way to speak of globally defined gauge potentials. But let's just ignore this for this talk about. We're just interested in the topological sectors. So all we need to know is what is the implied condition between the flux density and the charge here. And the implied condition is the following. So just focus maybe on the bottom line. If the first line seems confusing at the moment, the first line just says where our objects live. So the second line says on the left that from F2, from our flux density, we obtain this de Rham class, which is clearly in some sense topological deformation class of that flux, kind of measuring some totality, some topologically invariant totality of flux that we have. And on the right hand side, we can take this map that we have from X to CP infinity, first regarded by the above equivalence as defining a class in integral 2 cohomology, and then identifying via the de Rham map, or whatever you want to call it, that class in integral cohomology with a class in de Rham cohomology, right? So which is then denoted by a square brackets chi here. I'm going to call it the character of chi, for reasons that become clear in a moment. Well, actually, this is the analog of the character map, the Chern character on K theory, is the simple version of it, of the Chern character, just an ordinary cohomology. It takes integral cohomology to de Rham cohomology. Anyway, so the flux quantization condition that goes back to Dirac didn't quite say it this way, but it's equivalent to saying it this way, is that the de Rham class of our flux density cannot be any de Rham class. It has to be equal to the image of an integral class, which is part of the liquid data. So this integrality makes the total flux become an integral unit that quantizes it in this sense. Right here, so on the left we have total flux, on the right the charge character, and they must be equal in de Rham cohomology. That's ordinary magnetic flux quantization. So now the point is that this electromagnetic flux classifying space actually knows everything about the topological properties of the electromagnetic field. First of all, it knows that there are flux quanta, the integrality of flux quanta. I already mentioned this almost. Let's just make it explicit here. So the space of the cohomology class of our charges is now the connected components of this mapping space from our domain to CP infinity. And if we imagine we have a two-dimensional slab of material, as we do in these fractional quantum Hall systems, with a perpendicular direction and a time direction. But if we imagine that, as it is the case in fractional quantum Hall systems, that we want to be looking at solitonic states with respect to the surface, that is some little slab of material in our laboratory. So then the soliton condition means that fields have to vanish at infinity. So we have to adjoin to our R2, which is this slab of material. We have to adjoin to it the point at infinity and then ask for pointed maps that take the point at infinity to the base point in CP infinity, which is the zero element in CP infinity. So in a completely literal sense, actually, the fact that we're looking at map star, that pointed space to CP infinity, means that we enforce fluxes to vanish at infinity, which is the condition for solitonic fluxes. This is the correct condition to impose to see something like solitonic anions in the lab. And then after you adjoin the point to infinity to R2, it's topologically the two-sphere. So then we're mapping the two-sphere to CP infinity, and kind of by the definition there was an Eilenberg-MacLane space. Pi zero of that mapping space is the integers. There's integer worth of such maps, and that encodes the integer number of flux quanta. So here's a picture that comes from some textbook on Abrikosov vortices and superconductors, where the mechanism is the same. The flux lines will concentrate in integer units, and that is measured, that is kind of known by our classifying space. Have you chosen a different classifying space, it wouldn't be true. So in a sense, you could say here that flux quantization, this is often discussed in textbooks for magnetic monopoles, which Dirac was interested in, and then comes a long discussion that, magnetic monopoles haven't been observed, and few people, maybe nobody, except our review, highlights that, in fact, no, if you look at reduced cohomology with these pointed mapping spaces, then the exact same arguments that gives you the integral charge, integrally quantized charge of magnetic monopoles, gives you the integrally quantized charges of flux quanta through a surface. And that has been experimentally observed famously. You can make electron microscope pictures of these Abrikosov vortices and see them. Anyway, so this is encoded in the algebraic topology of that classifying space, CP infinity. But actually CP infinity knows more. It also knows actually the algebra of quantum observables, which is of topological flux through a surface, which gets to the point that I mentioned before, that the word flux quantization, which a priori seems to refer just to the discretization of flux, actually also goes hand in hand with the actual quantization of the topological flux quanta. Which is the reason for, I guess I'll show this in a moment, the reason for the title of our article, Quantum Observables of Quantized Flux, where the following formula is from. I guess I'm showing it next here. Here, this is our article, Quantum Observables of Quantized Flux, which observes that generally, actually for Young-Mills fields, not just for ordinary electromagnetism, the classifying space knows by formula, which I'll discuss now in a second, knows the quantum observables of electric and magnetic flux, ignoring here the observables on the potential, which is not something you actually want to care about in these experiments. Anyway, so what is this formula? So remember in the previous formula we saw that pi zero of the mapping space from our space-time to CP infinity to our classifier space gives us the number of flux quanta. And now pi 1, let's go through this formula. Pi 1 of this formula actually gives us the observable. So what are we doing here? So we have a surface sigma. That was R2 on the previous slides. Now let's take it to be any surface. Might be a torus, might be a disk, might be a punctured disk. And we'll keep adjoining that point at infinity to enforce the soliton condition. And then we look at the pointed mapping space in order to still enforce that soliton condition. And we take now pi 1 of that space. So pi 1 is the fundamental group. It's the group whose elements are loops in our space that are based at that start and end at a given base point, which is namely on the zero charge point. The map that represents the constant map on the base point of CP infinity that represents zero charge. So we look at loops which are like vacuum to vacuum processes in that mapping space. So we're in the vacuum, then some fluxes and anti-fluxes appear, do something, disappear again. And pi 1 is the group of these loops modulo continuous deformations, modulo homotopy of loops, called the fundamental group of a space. Computing here in our context the monodromy of flux, the possible ways of flux appearing out of a vacuum, doing something, and disappearing again up to topological deformations. And it measures what is possible there. And then the C here just stands for, it's the usual notation for the group algebra, the group convolution algebra of that group. And that turns the group into an algebra of observables. What it really means is that every group element becomes a generating observable, but then, as usual for observables, you'll be allowed to add them and multiply them as sums. That's all it does, the group algebra of flux operators. So that's a theorem here. That's a fact one can derive from the Poisson brackets of Yang-Mills theory, of Yang-Mills fluxes on surfaces. That formula could have been written down long ago. It was in parts, but there were left some gaps in this article I just mentioned, which we'll see next again. Goes the last step and concludes this formula actually. So this is a standard result that follows from just standard non-perturbative though quantization of the electromagnetic field. So this uses what is called sometimes refilled C-star-algebraic non-perturbative quantization of Poisson systems. These are the non-perturbative observables on electromagnetic flux. So let's look at an example. What does it mean on a torus, for instance? It predicts this formula. This predicts a standard prediction of what standard Dirac-Church quantization will imply for the fluxes. Well, and it says the observables are generated by two generators, two Wilson loop operators. One being the Wilson loop along one of the basis cycles of the torus and the other around the other one. I should have drawn a picture of these, but you've all seen these two cycles in a torus. So there's the Wilson line operator 1, 0 and 1, 0, 1, and you get the free algebra generated by them subject to the relation that they commute with each other, because that just comes out here. And that, of course, is not what you actually expect to see. Well, it is a little bit similar, but in fractional quantum Hall systems, you expect actually to see a deformation of this formula, deforming to the non-commutative torus. In fractional quantum Hall systems, Chern-Simons theory predicts that the actual Wilson loop observables form an algebra that is again generated by these two generators, the two cycles of the torus. But now the group commutator actually does not vanish. It produces a phase squared. Zeta is a phase, and that is the braiding phase of the FQH system, the phase picked up by the system as we braid two of these flux quanta, if we make them exchange positions. So this is the fractional statistics, if you will, the analog of the ±1 for bosons and fermions, in some way. Anyway, and its square is meant to appear here. So the upshot here is that the standard prediction of flux quantization for the electromagnetic field, going back to Dirac 100 years ago, is close to, but not quite, what you actually want to expect. Crucially, not quite what you actually expect to see in fractional quantum Hall systems. So what's going on here? How can we make sense of this? Well, we need to be thinking about exotic flux quantization laws. Apparently, we need to use another quantization law for flux, different from what Dirac said the magnetic field does 100 years ago, that reflects, accounts for the fact that in this fractional quantum Hall system some strong coupling effect goes on, which actually changes the behavior of the flux. So, given that I introduced this, or recall this definition of flux quantization in terms of classifying space, it turns out that now it's actually easy to generalize. That is the golden road to generalizing flux quantization. We work with classifying spaces. Namely, now once we've formulated all magnetic flux quantization with a classifying space, we can just think about changing that classifying space to pass to exotic quantization laws. So this is again really the content of this book we wrote, the character map in non-abelian cohomology, and then this encyclopedia article. Turns out, as explained and proven in these texts in some detail, turns out that every topological space actually serves as a classifying space for some system of flux species. And the character map is what tells you which system of flux species is quantized by a given topological space. So in our context, we could look at many spaces, but let's just try the two spheres. So at this point, this is just falls from the sky. That's just something we can try. Well, then we'll see that it actually matches lots of predictions, so that it's plausibly actually the right choice. But you should keep in mind that this is a choice at this point, and if at some point you find that some of the predictions that I'm surveying now are, or further predictions that I'm not surveying here, but which also follow from choosing the tooth sphere, that they, if you conclude that they actually disagree with what you see or want to see in an experiment, well, then you can choose a different space here. There's infinitely many spaces, topological spaces, classifying spaces, that will serve as classifying space for the same system of Bianchi identities. And if one doesn't match your needs, it's just like changing, adding a term to Lagrangian. You change your theory by adding, in this case, you add what's called cells to the space without changing its rational homotopy groups. But anyway, for the moment, let's just use the two sphere. So one motivation here for using the two sphere is that the two sphere is actually what mathematicians would call the two skeleton of CP infinity. Namely, CP infinity, we've seen is by definition the union of all the CPNs. But let's just look at the first one, CP1. That is the Riemann sphere with its complex structure. But the complex structure doesn't play a role here. Just the topology as such is just the two sphere. So the two sphere, in a sense, is the first stage in CP infinity, and the rest is sort of addition to the two sphere. You obtain CP infinity by starting with the two sphere and kind of removing something by adding these cells. So this is a little counterintuitive, but a well-known phenomenon in topology, that as you make classifying spaces larger, some of the properties can actually go away. You stabilize things. And here we will be looking now at the unstable version of CP infinity in some sense. Then here's a fact, which is explained in these references that I mentioned here. It's just a fact. The two sphere serves as possible potential classifying space for electromagnetic flux with Chern-Simons flux in the following sense. There's a character map that takes kind of charges in 2 homotopy, as we say, maps to S2, takes them to the following de Rham cohomology data, non-abelian de Rham cohomology data, given by differential form data. So there's again a closed differential 2 form F2 just as before. So it sees magnetic flux as before, but it also sees a higher flux, a 3-form flux, a high gauge field, if you will, or the flux of a high gauge field, the flux density of a high gauge field. And that flux density is not closed, well, not generically closed. It instead satisfies a nonlinear Bianchi identity, saying that its de Rham differential is actually the wedge square of our magnetic flux. Well, that is exactly the defining characteristic formula for Chern-Simons forms. That is the original definition, essentially, of Chern-Simons forms. Given a gauge field flux, Chern-Simons form is a 3-form that serves as a co-boundary for the first Chern form you can form from your flux density. See, in the abelian case, this just means it's a co-boundary for the wedge square of our flux density. So, in this sense, the two-sphere, someone knows that something like Chern-Simons theory is going on. This result is really originates in our article to historical blah 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 and so forth, which again was an article in high energy physics and M theory discussion, which need not play a role for us here. It's just a mathematical fact, but the way we originally arrived at it involves this Chern-Simons form also appears in what's called the Green-Schwarz mechanism in heterotic M theory, and in fact more generally and for branes on A1 singularities and so forth. But it doesn't matter. There's just one way of embedding this whole story here into M theory if you wish. If you don't wish, then just don't have to think about this. So the way this works here, this character map in general, this map that assigns differential form data to maps to a classifying space, is that flux species on the right correspond to the free homotopy groups of the classifying space that is used on the left. So what this just means in our context is the following. So CP1, our new classifying space, has a non-trivial homotopy group in degree 2. It's kind of the group of two-dimensional deformation classes in CP1, and that is the integers, so by the Hopf degree theorem, if you will. So we call it the unit class, and as we actually go, if we were to re-embed CP1 into CP infinity, to the original classifying space, that unit class would survive. That pi 2 is the same pi 2 that you also see in CP infinity, and that will correspond, or that does correspond to the fact that we see F2 there in both cases. Previously for ordinary magnetic flux, and now we still have a flux density F2. But now, in stark contrast to CP infinity, which as a KZ2 has no other non-trivial homotopy groups in positive degrees, there is a non-trivial non-torsion homotopy group of CP1 of S2 in degree 3, famously known as the Hopf generator, right? There's this non-trivial map from S3 to S2, topologically non-trivial map called the Hopf vibration. And that represents the non-trivial unit in the integers regarded as the third homotopy group of CP1. And that class does go away, or would or will go away, as we were or would re-embed our CP1 into CP infinity. So in this sense, this new guy, this Hopf generator, that is the new topological class that is predicted to somehow affect our system as we decide that it's not described by flux by ordinary direct charge quantization, but by this exotic quantization modeled by S2. So here's again the map. The flux density F2 comes from this unit class, or corresponds to it, under this character map, or under the Sullivan theorem, whatever it's called, and a new class, a new flux density H3, a higher flux density, reflects the presence of this Hopf generator. And this will recur in the following slides. We'll keep seeing that the Hopf generator in pi 3 of S2 is what gives rise to all these exotic aspects of fractional quantum Hall system. That's what sees the braiding phases. We'll see that in a moment. So it's quite curious here. What we're dealing with is not quite ordinary Chern-Simons theory. In ordinary Chern-Simons theory, this H3 here is not a flux density, but it's a Lagrangian density. In contrast here, we're not even talking about Lagrangian densities. We'll be setting up a non-Lagrangian theory, because remember the previous formulas you had, they got us to the quantum observables. I'm scrolling back here. To the quantum observables without ever even writing that, just directly, without writing down a Lagrangian density, without then, fixing it in various ways to make it globally defined, and then finally quantizing it and waving our hands. No, we just immediately got this formula, by ways that were explained in this article here. And so we will not encounter any Lagrangian density at all. But nevertheless, we see something close to what is involved, structure close to what is involved in defining ordinary Chern-Simons Lagrangians. But with the ingredients entering in slightly different grounds here. H3 is now a higher flux density. And we'll keep seeing this now in the consequences. We'll see that a whole lot of the fine printed predictions of abelian Chern-Simons theory actually reproduced very directly. They just come to us. In fact, in regularized form, you'll see it. What we have obtained here is kind of a way to redo quantum Chern-Simons theory in a really efficient way. But we'll also find actually in the course of that some slight differences, or I would say corrections to the standard law of abelian Chern-Simons theory. Anyway, so we'll get to this. Okay, now remember, after we understood now what the rules of flux quantization are, we wanted to make a hypothesis what the correct flux quantization law is. Well, we almost said it already here. We're going to look at the two-sphere. So concretely, it now means the hypothesis size, concretely plugging this into our formula, it means that the hypothesis now that fractional quantum Hall flux observables are actually the group algebra of the pi 1 of this point mapping space from the one-point compactification, as it's called, of our surface, to what? To this new classifying space, which is just CP1 instead of CP infinity. Right, so here CP1, S2 is just plugged into this formula, which previously we saw for ordinary direct charge quantization is just CP infinity. So we're just changing the classifying space here in that formula. It's a very simple, conceptually very simple change in that formula. And that implements the exotic flux quantization. And so we're calling this hypothesis lowercase h here. This is hypothesis, actually a little cousin of the hypothesis h in supergravity that we considered originally, which actually led us to all these considerations, where a completely analogous argument is done for the proper flux quantization of the electromagnetic flux, but of what's called the C field flux density that lives in 11-dimensional supergravity. There, an analogous argument shows that a consistent flux quantization law for the C field is actually given by the force sphere, or some twisted version of it. And that in turn, just to briefly recap the story, which really is behind the hood, under the hood here, that in turn induces a certain flux quantization law on the M5 plane, on M5 plane probes. And if you then orbifold these probes and use an equivalent form of flux quantization coming from an equivalentization of this force sphere, going to fixed loci on this Orbi singularity anyway makes the two-sphere appear. This comes really as a fixed locus of the Penrose. Anyway, so there's some story which is described in the articles I listed previously. Anyway, so in this sense, this hypothesis lowercase h here actually follows from geometric engineering of FQH systems on M5 branes, by assuming that the ambient C field of these M5 bits in turn is flux quantized in a compatible exotic cohomology theory. But again, please ignore if you like. Here's just the references. So this hypothesis H goes back to Hisham Sadi's article, Framed M-Brains, and then was formulated as such in our joint article, Twisted Cohomotopy Applies, blah, blah, blah. And so we have a whole list of articles on this subject. But so anybody who's interested can look into this, but for the present talk, it doesn't matter anymore. Here's the one article that kind of connects this high energy supergravity story to the onions that we're going to be interested in by geometric engineering. Again, you do not need to know this. So, okay, let's just improve this formula just a little bit. So, in previously stating this formula, I stated it as for kind of ordinary field theories. Now we want to remember that we're actually dealing with a topological field theory. Certainly we're interested just in the topological aspects, but we also want to be thinking of it as a topological field theory, just like Chern-Simons theory, and as such it has to be generally covariant. And that means, in math terms, that all our observables should actually be made equivariant under the diffeomorphism action. So that means that instead of looking at pi 1 just of this mapping space, which is just the space of topological field, solitonic field configurations of our system, we should actually identify up to gauge transformation any pair of such field configurations if they differ just by diffeomorphism on the base space. So in abstract math and algebraic topology, this means that we're looking not just at the mapping space, but at its homotopic quotients. That's what's indicated with a double slash here. The homotopic quotient by the diffeomorphism group. But since we're just computing pi 1 of that, it simplifies to the statement that our pi 1, our flux monotomy group, is turned into the semi-direct product with pi 0, the connected components of this diffeomorphism group of our surface. And that is famously known as the mapping class group. The homotopy or isotopy classes of these diffeomorphisms are called the mapping classes because they're maps from sigma 2 to itself. And so we're actually going to be using this as the definition of the generally covariantized observables. It's the flux monodromy acted on by the diffeomorphisms to encode diffeomorphism invariance or equivariance of everything. This is going to be important, particularly to get the right topological order and ground state degeneracy. This encodes this on the torus. The mapping class group is of course the modular group, and this will encode modular equivariance. So modular equivariance is a shadow or special case of diffeomorphism invariance on tori. And so, then in summary, the statement is that the hypothesis that we're going to be investigating now is that the quantum state spaces of our fractional quantum Hall topological fluxes, well, there must be the modules over the course the algebra of observables on the top of the slides. But since the algebra of observables is a group convolution algebra, it means the modules over it are just representations, equivalent representations of their group. So the statement now is that the exotic flux quantized solitonic fluxes here have spaces of states over a given surface that are unitary representations, irreps in the superselection sectors of this covariantized flux monodromy group. That is shown on the bottom here. So that's our theory that we're going to be investigating now. You see, it's a purely algebraic topological formula now. It cuts right to the gist of the system. There's no differential geometry, blah, 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 the whole story. There's no geometric quantization going. We're going right to this formula here. It tells us exactly what the quantum states are. Now we can just unwind and see, does that match observation or not? Does it predict something or not? So this is a novel effective theory of fractional quantum Hall systems. It's non-Lagrangian, it's non-perturbative, it's globally well defined. All in contrast to usual approaches. Where about the first 2 points you might say, well, okay, so what's the gain in itself? But the third point is an important one. This is actually globally well defined, and then the first 2 points come with that. That works by not using a Lagrangian, which always just uses local data, and by not using the usual quantization methods. Okay, so predictions are followed by rigorous analysis. So first we use algebraic topology to compute these flux monodromy groups, pi 1 similar product mapping class group, and then we use representation theory to classify the irreps of the groups that we obtain this way. So let's just check now the predictions of hypothesis lowercase h, little hypothesis h. So before we get to checking things on specific surfaces, here's a general remark on what spheres classify in respect to with respect to fluxes. So the key driving fact here behind really all the following theorems in some guides or other is the ancient Pontryagin theorem. Before it was called the Pontryagin-Thom theorem, that is as it is famous now. Pontryagin already long before, more than a decade before, Thom had the unstable version of his theorem, which is actually the one that matters for us. The Pontryagin-Thom theorem is just in a way just the linearized version of what we're dealing with here. Anyway, so the classical Pontryagin theorem says or entails that spheres, regarded as classifying space, generally classify, if we are evaluating on a manifold, on a smooth manifold, classify submanifolds Q with normal framing NQ. What does it mean? In just a moment I'll rephrase this as a statement about flux quanta, but just bear with me for a second on this statement of the classical Pontryagin theorem. So the sigma here, somewhat lonely and easy to miss, is meant to label our ambient manifold, which you can think of as being the screen here, that our blackboard, our whiteboard that we're seeing here. And so let's see, in one direction the Pontryagin theorem says if we had a submanifold, or if we have one, a brane if you will, or a soliton here, soliton core, indicated by this black line, regarded as a submanifold of sigma, excuse me, and called Q. So if this has a normal framing, which means, roughly, so it means that we have a tubular neighborhood coming from a trivialized normal bundle. So intuitively that means that at every point of Q, as we approach that point from outside this manifold, as we come close enough, as we are inside this tubular neighborhood, there's a unique normal directed distance singled out. So there's a vector that we can find that tells us how to go straight to our manifold, or conversely it tells us once we're inside this region, it gives us a directed distance of our point that we are at from the manifold. So that means, conversely, that at every point of the manifold here, the points around it map uniquely to a copy of R, copy of a Euclidean space, which we can think of as being, in this picture, as being mapped to this open neighborhood of one point in a sphere. And then we can think of it as actually being, we enlarge that and actually wrap it around the whole sphere. Let me just drink something to get my throat. So that, in fact, we regard, if also the sphere on the right here is regarded as being the Euclidean space, of the corresponding dimension with the point at infinity adjoined, that we're mapping this tubular neighborhood, we're identifying it for each point in Q with that corresponding Euclidean space, and regard all other points in sigma that are farther away as being at infinity. So in this way, we're actually mapping a submanifold equipped with this normal framing, which will be a reflection of the charge carried by the submanifold with a map to the spheres. In this way we get, so this is a map defined on all of sigma, right? Because far away from our submanifold on sigma, it sends everything to infinity here. But as we come close to the manifold, we see that stuff wraps around the sphere. That's the incarnation of the charge. That's the homotopy charge of our manifold. All right, so that's the standard story of the Pontryagin theorem, reviewed by Pontryagin a long time ago. And now we just observe, which we did in these articles here, but never mind, we observe that as we think now of the sphere as classifying solitonic fluxes with exotic flux quantization laws, that the same story actually can now be understood, the submanifolds can be understood as soliton cores, and these tubular neighborhoods as flux concentrations around them. This is indicated in this cartoon here, which is the relevant one for our setup. So we're on our surface here, this two-dimensional slab of material in our fractional quantum Hall system. And in one direction, as we single out soliton cores here, which are now just the vortex eyes of the eyes of the vortices, where these flux quanta sit, with a certain dimension of this vortex here, where the magnetic flux is concentrated. Remember the previous picture of how the flux lines concentrate and go through regions. Forming these Sabrikosov vortices. Anyway, so given such a configuration, we obtain a map to the two-sphere in our case, that sends all of the surface here to the point at infinity, not even shown on the slide here of the sphere. And as we approach any of these vortex cores, we start mapping the vicinity of these vortex cores over onto the sphere, so that every yellow flux quantum region here gets mapped once around the sphere. So that means if we have n flux quanta here, the map, the classifying map that we're constructing has degree n. It wraps n times around the 2 sphere, and that is how the total charge is encoded. And then Pointryagin theorem tells us that this actually goes in both directions. Conversely, if you have a map to the 2 sphere, it's always homotopy equivalent to such a situation, and so forth. So this sense, kind of curiously, spheres are, as classifying spaces, actually singled out physically even. They are exactly the classifying spaces that, in a precise sense, exactly see branes as being the things that carry charges under this flux quantization, namely submanifolds, cobordism class of submanifolds. And then, well, anyway. So, let's now look at let's now actually analyze the various quantum states that we find. So first case is we're on the plane. So in laboratory this will mean we're on the disk. We have a slab of material that is disc shaped, or it can be rectangular shaped. The topology, I mean the exact geometry doesn't matter. Only the homotopy type, in fact just the homomorphism type of this thing. Anyway, so we're on the plane, so that's the simplest setup we can have in the lab. And we want to see that we can actually derive the predicted, or the hallmark fractional statistics of fractional quantum Hall systems in this situation. So what does our theory predict? So remember, we want to be computing pi1 of the pointed mapping space from the 1-point compactification of R2 to the 2 sphere. So pi1, remember, there was a homotopy class of these loops. So before we pass to the homotopy classes, let's just look at all these loops. So omega means the loop space based at the base point, the loop space of the space of pointed maps. So these are the actual processes of flux coming out of the vacuum, doing something, and going back to the vacuum before we have quotiented out topological deformation classes. And now the theorem says, going back to a very classical theorem by Graham Siegel from 1973, says that this loop space has equivalently as points the elements in the space, so the elementary flux processes are actually, the vacuum to vacuum process are actually framed links, which in the standard way we bring to paper like this. So remember, previously we saw with the Pointryagin theorem how these flux cores form these points here, and now that we're forming pi1 of this space, we see these points are moving around. If we read the time moving up here, going up here, then we're in the vacuum here, then suddenly anion, anti-anion, flux, anti-flux pairs appear, move around, do something, braid around, pinch around each other here, to eventually disappear into the vacuum again. So this framed oriented link, which is a loop in this space here, by Siegel's theorem, so this is not meant to be obvious, but I'm just telling you this is the case. So this process is one loop in this space. But then in this space also now has paths between these loops, which are the topological deformations. So the curves in this space are these wiggly arrows here. It turns out these curves are actually link cobordisms. So they involve usual local isotopy and Reidemeister moves, but also link cobordism. So we can deform, or in this space, the topology that is encoded by this space knows that as we deform these vacuum to vacuum processes in such a way, the observables on them actually remain the same. These yield observationally equivalent processes. So here I applied a saddle move, so the link cobordism, to this area of the link diagram, which kind of reconnects it like this, and then we can further apply such saddle moves to see that it actually is also equivalent to this one here. So that is the statement that the curves in our space are link cobordisms, so that such a process, which is one process in our space of processes, can continuously be deformed to this process. And what you see here is that in the end it doesn't matter actually how these fluxes actually braid around each other. All that is retained, in the end we have just an unknot here, a framed unknot. All that is being retained is how often the net number of self-crossings that we had. Everything else changed. And this is going to be a reflection of the fact that we're dealing with abelian anions, meaning that the precise braiding is not actually reflected by the abelian anions except from the total number of crossings. For each crossing, there is being picked up a phase, as we'll see in a moment. So remember, the actual observables were predicted to be pi1 of this space, not omega, so just the deformation classes of these processes that we just shown. So as we now map a framed link to its deformation class, so to pi1 of this space, what does it become? And the previous picture was, if you look at our article where we prove this here, a billion anions in M5 branes. I don't think I'm linking to it here, but anyway, that's the article. A billion anions in N5 branes. We prove that this means, which is kind of obvious from this picture already, that the homotopy theoretic class of this process is encoded in the net number of its self crossings. That's called the rith. I don't even know how to pronounce this, to be frank. That's the total number of self crossings of a framed link, and it's an integer. And so here's an example. Here's the hop link. Has total crossing number plus or minus 2, depending on how it's oriented. The trefoil node has plus 3, and so forth. And so one can then compute that these were the observables, the algebra of observables. You see what I'm saying here is the algebra of observables as such is just the integers, but they're actually labeled by framed links. So every framed link gives an observable in our system. That's just the situation with Chern-Simons theory, where framed links, regarded as Wilson loops, are observables on the system. That's exactly what we see. So we can just compute the pure GNS states on this algebra, this very simple looking algebra of observables. And one finds by elementary arguments that these states are labeled by phases, elements of U1, zeta, such that every Wilson loop here, every framed link, has as expectation value in this state the exponent of the power of zeta taken to the power of our total crossing number. And interestingly now, if you just rewrite the total crossing number as in traditional form as the sum of a linking number between different connected components of our framed link and the number of self intersections, called the framing number of every component with itself, then in this form you recognize this is just the way that standard textbooks on Chern-Simons theory will tell you this is just the formula for the the Wilson loop observables in a billion Chern-Simons theory. So this recovers exactly the result of a billion Chern-Simons theory, including actually, this is kind of remarkable, the framing regularization, because actually plain Chern-Simons theory does not predict this. If you really just follow your nose in Chern-Simons theory, you get infinity. You get a non-well-defined result, and it's an old step due to Polyakov. I don't have the reference here on this page, but he already said, okay, all right, it's one of these things. Oh, it's anomalous, so we need to fix it. So the theory itself is actually inconsistent. If you just take it at face value, Chern-Simons theory, just doing this integral for the propagator of Chern-Simons gives an ill-defined expression. And then people say, okay, after the fact, things are being corrected. They say, oh, right, let's, instead of just taking links, which seem to be the right description of these Wilson loops, let's give them a framing, and then we can deform the link a bit and add a self-framing, and this all this story discussed, and then in the end they come up with this formula. And this is now, it's clearly the right formula, but I'm just saying it's not systematically actually derived from Chern-Simons theory. So Chern-Simons theory gives something ill-defined, and then you wave your hands to argue that what you really wanted is this formula. So you would hope that in a proper, non-perturbative, well-defined theory, this formula just drops out right away without you having to wave your hands. And that's exactly what it does here, which I think is a good sign. The key point for us anyways, for fractional quantum Hall systems, is that this means, if we unwind this formula now, it says that for every crossing, you pick up one power of zeta, positive or negative, depending on the orientation of the crossing. So if we have a complex links diagram, it says as we form this expectation value for each crossing, we pick up one factor of zeta. And that is, of course, exactly the story of a flux quantum braiding phase that you want to see, that is being seen, as I cited at the very beginning, by experimentalists since the last 5 years. This is actually observed. And this is the hallmark, of course. This is the abelian anionic fractional statistics seen for solitonic anions in fractional quantum Hall systems. But by solitonic here, you see, we'll notice we see very vividly here that even though we do see anions in their braiding phases now, there's no way that you could now take this prediction and declare that you can actually grab such an anion, or grab actually two of them and start moving them around each other. All it says that they are somehow there. And that's in fact exactly how this experiment works. They do these Fabry-Perot interferometry experiments and conclude that somewhere in the system there must have been some number of anionic flux quanta, but you don't know where in the system, and you certainly cannot grab them, and you absolutely cannot grab them and then in a controlled way turn them around each other. So this is a important and clear reflection of topological order in our system. And it says the system is topological and is topologically ordered and anionic, but it's not sufficient yet actually for doing topological quantum gates unless you trick yourself, as I think some people do actually. This alone just tells you, okay, this is a promising road, but we need more. And at the end of this talk, of course, we want to be seeing how to actually get defect anions that are non-abelian and controllably braidable. Okay. All right, here, so I'm just summarizing this again. So the fact that we have these flux quantum braiding phases really comes from the fact, right, so I didn't actually mention this properly. Let's think again, why did we actually know that this pi1 here, in our case, the flux observables actually formed Z, the integers? Well, this was really just the argument of the Hopf generator again. You see, pi1 of a pointed mapping space is the same thing as the pointed mapping space of the, of the suspension of this space. Pi1 can be taken to produce the suspension of this space, but the suspension of this space is the 3-sphere. So this just comes down to, again, computing the pointed maps from the 3-sphere to the 2-sphere. And as we just said before, that is the free abelian group generated by the Hopf generator. So it's again the generating plus minus 1, the integers here, that is again the Hopf generator. So we see again that it's the Hopf generator, the element that disappears if we would go back to our standard classifying space, which encodes this braiding phase. All right, let's move on. Second case, the torus. The torus is not easily, or maybe not at all, realizable in experiment. I mean, maybe you can, well, at least it's subtle, let's say. The torus with transverse magnetic field, at least it's subtle. I don't think it has actually been realized. It's not clear how to do it. So, what does our theorem predict? This is curious. It goes back to an ancient theorem from 1974 by Hansson, a Swedish, or Scandinavian anyway, mathematician who computed these things many, many years ago. For some reasons, he was just interested in them. It's curious how many of, like when you do these things now, it's these ancient results from old school algebraic topology that really didn't mean anything, or not much. But when they were proven, they were just kind of exercises in computing. They suddenly gained this deep significance. So using that result, we find now actually Hansson's result, even though he would have had no idea that this is what it's saying, but you just take his article and you see it actually says that our flux monotropy group pi1 on the torus to S2 is again generated by these two Wilson loop observables and now subject to this deformed non-commutative group commutator law, which says that as you commute these two Wilson lines with each other, they actually pick up the square of a phase. Kind of remarkable. So the non-commutative torus appears as quantum observables with exactly the correct form that is expected for FQH systems. It's just a fact now. It's just a fact of algebraic topology. But now it gets interpreted in our new flux quantization as producing the algebra of observables on the torus. So this means that the finite dimensional irreps, well, it doesn't mean that, sorry, this is a second step in the theorem. So we also prove in these notes that I'm reviewing here, that the finite dimensional irreps of this algebra here that extend to the covariantization by diffeos, which remember over the torus means that we're modularizing, and we're going to be looking here, we should be looking here at the covariantization with respect to diffeomorphisms that are actually spin diffeomorphisms that preserve the fermionic, the antiperiodic AA spin structure on the torus, the one that is suitable for fractional quantum Hall systems whose fundamental constituents are electrons. So it's kind of curious that the theory actually sort of retains that information about the fundamental nature of the fractional quantum Hall system here. So anyway, we're modularizing with respect to the spin modular group, and it turns out the finite dimensional irreps that of the flux monodromy that do extend, that are modularly equivalent, have a braiding phase a primitive root of unity. Remember, so in the previous argument on the plane, we just got that there is a braiding phase. It could have been irrational at that point, but now it's in fact identified with this braiding phase here. One can show that these are identified as zetas. There's a reason why they're both called zeta, and it actually has to be a primitive root of unity. So this is the actual fractionalization now of the braiding phase. And second, it has dimension q, the denominator here. So this gives us the ground state degeneracy. It's at this point actually that there's a slight discrepancy here at non-unit filling fractions. If p is not equal to 1, plus minus 1, then for some of these hierarchical states in K-matrix Chern-Simons theory, the ground state degeneracy, well, it's always the square root of the determinant of the K-matrix. It's not just Q in general. But on the other hand, also, of course, Chern-Simons theory generally predicts that this is the algebra of observables here. And you see in the second step, so it's only the first step here that uses explicitly our exotic flux correlation. And the second step is just, this is the algebraic topology. The second step is just a representation theory applied to this statement, which would be the same for ordinary Chern-Simons theory. And there's just no wiggle room here. This just says that the finite dimensional irreps that are modularly equivariant have this property. So it makes me think that there's actually a gap in the standard. So in as far as K-matrix Chern-Simons theory disagrees with this, it looks to me like that's the fault of K-matrix Chern-Simons theory, because this is just a mathematical fact here about irreps. Anyway, so this is what our theory predicts. So, remarks again, the proof shows that the braiding phase, zeta, again comes from the Hopf generator, I mentioned this before, that fractional quantum Hall system must be described by spin Chern-Simons theory. So this is encoded in this fact here that actually we're using the spin diffeomorphism structure. If you don't do that, if you consider the full modular group, which is the spin diffeomorphism group of the PP, the periodic spin structure, then you actually find that zeta is furthermore constrained so that either P or Q, they have to be co-prime of course, but either P of Q then has to be even. And that turns out to be exactly the right condition for bosonic FQH systems. This is maybe a little known fact. There's also bosonic versions of the fractional quantum Hall effect. We can take a Bose-Einstein condensate consisting of bosons and rotate it rapidly. The rotation then acts as an effective magnetic field for these bosons, and if these bosons have repulsive point, how's it called? Repulsive point interaction, which mimics the Pauli exclusion principle, then it turns out that these bosons actually will show a fractional quantum Hall effect. And the filling fractions of these bosonic FQHs are in fact just those that we get here for the even spin structure, where either P or Q is even. So the principal series of the bosonic fractional quantum Hall effect is not 1 over 2p plus 1, but or p over 2p plus 1, but is p over p plus 1. So either p or p plus 1 is even. And it's interesting that our theory sees exactly that fine print distinction, which you will not even see discussed, I think, in the standard literature. Right, which is this point 3 here. Okay, so third case, the open annulus. Let's see how the edge modes arise. So now we just keep playing our game. We just apply algebraic topological analysis to this mapping space. Let's go to the annulus. I hope I have a picture of the annulus here. So the annulus is this disk sort of with one more hole in it called A2. So we join this point in infinity and we compute this group. Turns out it has these two generators. There's a new phase here, psi. We'll see it's not zeta, it's different. And then there's sigma. Sigma is kind of the diffeomorphism that swaps the two boundaries, the two edges. And it says for some relations. And classifying the finite dimensional irreps compatible with this map, there's actually this canonical map here from our annulus back to our surface, which can be used to compare we found the generator of the braiding phase here, so we can pull it back here and see what is the generator of the braiding phase here. And we find that, well, this psi, there's a phase guy here, there's a generator here whose representation in an irrep, it will act as a phase. This will act as the multiplicative difference between two phases associated with the inner and the outer edge, such that zeta, the actual braiding phase, is the product of these two phases. And if you compare this to the fractional quantum Hall literature, you see this is exactly the relation that is satisfied by what is the momenta, sometimes called the fermion momenta, the exponentiated fermion momenta of the edge modes that are meant to be running around chirally, meaning in one direction, around the edges of such a fractional quantum Hall systems. And there's as you form this product here, This product in this context is known as computing the tunneling current of quasi-particles from the inner to the outer boundary, and that being a current of quasi-particles, it actually has to be a fraction of the actual electron current. And as you exponentiate that statement, so we just see the exponential version of it here where everything is phases, it's precisely this relation that our braiding phase zeta is kind of decomposed now into these two Fermi momenta phases. And interestingly, the other generator, so this is kind of, in this sense, in this way, we see the edge modes, at least the zero modes here, the global moment, the center of mass momenta they have. But we also see a bit more, which is, well, it seems like some references kind of see this, but if you work out now the irreps of this group, so the interesting thing is this little group here is actually non-abelian. It's just Z, semi-direct product of Z mod 2, so it's a very little group, but it's actually a non-abelian group. That means in general it has irreps that are not just one-dimensional. It has higher-dimensional irreps that are non-abelian in this sense, have ground state degeneracy. In particular, this is one, just by analysis, one finds this has 4 one-dimensional irreps and a single two-dimensional irrep. And which appears if these phases are actually not the same, which is a case that doesn't seem to be considered much in the literature. So there's already a first prediction here. It says if the Fermi momenta of the chiral currents, the chiral edge modes, are actually different, then there's ground state degeneracy already on the annulus. So there's already a topological order on the annulus. I can give you, I'm not citing it here, but there's at least one article that predicts ground state degeneracy on the annulus if you connect it to superconducting regions, which these are here, because our magnetic field is expelled from being outside of the annulus itself. The formula that these authors give seems different from the formula we have here, but at least it's, so this seems to be another discrepancy to the literature, which this could be, so as opposed to any statements about the torus, which is really hard to realize in experiment, this is the standard case that can be realized in experiment. Slabs of FQH materials to the electron gases on an annulus. This is what people discuss routinely. As here the prediction would be if you can somehow arrange your edge modes to have different Fermi momenta, differing in magnitude, not just in direction, there should be twofold ground state degeneracy. Okay, so let's take stock so far, and then let's come to the main prediction, even though we just saw already predictions already creeping in here. So these results show that the hallmark properties of FQH systems are reproduced. Fractional statistics, topological order, and edge modes. Up to some subtleties. So the ground state degeneracy, as I said a few times, for non-unit filling fraction may differ from predictions of K-matrix Chern-Simons formalism. So this means that we're both supporting hypothesis H here. It meets the standard properties, but it also makes it testable in that there is potentially measurements that can actually distinguish hypothesis little h here from standard effective field theory. But we can go further now. The hypothesis H goes further to make predictions now about surfaces with punctures. We haven't considered this yet. And these punctures model fluxes spelling defects in FQH materials. Maybe I'll say this again as we see the picture. So here's the fourth case, the fourth and last case, and then I conclude. Let's take the two punctured planes. I'm denoting it here in this maybe somewhat non-standard but suggestive way. It's the plane R2, taking the complement of 2 points. So 2 is the boldface 2 means to be the set of 2 elements. We're removing that from R2, 2 punctured plane. And we're going to see para-statistical defects. So again, we can just compute stuff. So remember, this is our formula for the algebra of observables, flux monodromy, pointed maps from our one-point compactified surface to S2, homotopy quotient by the diffeomorphism. Turns out this is actually a subgroup, what's called the framed symmetric group on 3 elements. Framed symmetric group means it's like a frame braid group that all of the 3 strands is equipped with an internal way of twisting around itself by full rotations, so that each of these strands carries an integer number. So the framed symmetric group, I'm not showing you on the screen, but it's the semi-direct product of the symmetric group acting on Z3, 3 copies of Z. But we see the subgroup, curiously, so the framed symmetric group might be what you expect if you, for instance, believe that Rethinking to Rav theory describes, first of all, Chern-Simons theory, and as such, then fractional quantum Hall systems. But curiously, here actually we see a subgroup of frame permutations that have total framing divisible by 3, which I've searched for this a bit and asked some authors. This does not seem to be a constraint that has been observed or noticed or discussed before in either Chern-Simons or fractional quantum Hall systems, even though the analogous constraint was already used actually in the previous result, which is actually the analogous statement for Sim2. This already entered here, so we've already seen it in action in a way. This is explained in our article more that we just said here. So, okay, here's the picture finally. I should have maybe shown this earlier. So R2, without 2 points, looks like this. It looks like we are on our disk material and we've removed 2 regions. And remember what we're doing here is we're adding this point at infinity and looking at pointed maps. So the point of infinity identifies everything that is at infinity, which for us now is all the edges here, because we've just removed the points. So these edges are open in the sense, not maybe well indicated by this figure here, because I had to draw these arrows to indicate that these edge modes. But it means as you're approaching the edges of the system, actually you're approaching this point at infinity, but we're actually classifying fluxes that vanish at infinity. That means all the fluxes actually have to vanish in the white regions. So the white regions are flux expelling. Right, what I'm saying? Right, to make clear what's going on here, we have a math formalism and we're matching it to the physics. We're saying, well, if you have physics that is represented by this mass, punctured surfaces, so then it must be physics that describes flux expelling islands inside fractional quantum Hall system. And as such, we're now making predictions about such situations. And then, of course, what is a flux? How can you make a flux expelling island in a in a semi-conducting fractional quantum Hall system? Well, you could make this a superconducting region here. Dope it, or otherwise make it superconducting. This is actually known. This is a standard discussion. It actually relates to this idea of these Mariana zero modes, which is a similar setup in 1D. So here we're seeing it actually in 2D, where semiconducting, superconducting interfaces, heterostructures, are considered. And so the superconducting activity by this Meissner effect would expel, unless it's broken by the strong magnetic field, but if you can retain it, it will expel the magnetic field from these white regions here. And then again, we work out the irreps here under the previous assumptions. We find that there's phases associated to all these edge modes. And now we find, as you compute the irreps of the subgroups of frame braids, you see there's 2-dimensional representation, which of the symmetric group on 3 elements, semi-direct product with these framing phases. So there's a 2D, if you will, para-anionic statistics being predicted here. Para because we're seeing actually a braid representation, as we will, on these 3 strands, right? So these is 1 strand, 2 strand, and then there's sort of the outer strand that actually factors through the symmetric group. I find there's maybe some, how should one say, maybe some confusion in the literature, or at least it's not brought out properly, that the para-statistics is being discussed from various points of view, and people, they try to identify it with a fundamental symmetry. That's not what we're doing here. We're just looking at, we're just seeing braiding phases, like anionic, berry phases, resulting from the adiabatic braiding of onions around each other. And we're in the situation where the braid group on 3 strands actually factors through the symmetric group. And one should note actually that, call it para or not, this means that we actually have even more topological protection than for generic representation of the braid group, because the braid group says if you have a representation of that, if your physical system represents that, then it means, oh, okay, the physical system is invariant under isotopy of these braids, which is a strong topological invariance condition. But if that representation actually factors to the symmetric group, it means the system is much more stable. Even you could even cross these braids through each other, which kind of a dramatic thing for usual braid representation. You could even do that. That would not change the phase. That would be, your quantum gate would be stable even under such drastic operations. It would only depend on the endpoints of these paths. So in a sense, these para-anions actually way more stable, even more topological than standard topological anions. So this would be interesting if this were actually realized in nature. In the article we also compute which quantum gates you actually find in this 2D rep. You find rotation gates by 1/3 fractional degree angles, and you find a Z-gate. So you find stuff that you would actually need for standard quantum computing routines. Rotation gates are used all over the place for quantum Fourier transforms. And if you could realize this prediction here that we're just making in the lab, well, first of all, you would have to look for it. I don't people have looked for it before. You would be able to realize an important rotation gate and stabilize it. It's a non-Clifford gate, actually, that would be predicted here. This is a topological realization of a non-Clifford gate, which is something that other approaches are struggling with. So this is a prediction, and it just keeps going from here, even though I haven't I don't show more slides on it now. You can now consider the n-punctured plane, and then you get subgroups of the framed braid group on n strands. It's actually the framed spherical braid group that appears here in general. But anyway, of a framed braid group on n strands, and these of course have now all the possible complicated irreps in the world, right? You can then use all your representation theory of braid groups to predict, would be candidates for possible braiding phases that you could observe here. Okay, so now to conclude finally. Oh, here's right. I have a slide here, the n-punctured, but it doesn't say anything else. Okay, let's conclude finally. This was too long already, I guess. So, to recapitulate what we said, fractional quantum Hall is a candidate for topological quantum hardware if the anyons could be made controllable. Fractional quantum Hall anyons are effectively just exotic flux quanta, which is a curious point to be highlighted. It's kind of obvious, but rarely highlighted. But the standard effective Stern-Simons theory does not actually reflect that well, or not at all. So let's turn the situation right side up. Exotic flux quantization should be applied. A candidate such law does exist, hypothesis lowercase h. So it turns out this actually rederives all the hallmark properties of FQH anyons. But it also predicts anyonic defects where flux is expelled. So, topological quantum computing via superconducting doping of FQH systems seems to be a possibility that is predicted by this novel theory of the fractional quantum Hall system. And that might be, if that could be experimentally realized, so, and this theory gives now incentive to look for certain effects, to look at these superconducting islands inside semiconducting fractional quantum Hall system and see if they give rise to ground state degeneracy. So this could be checked. In any case, exotic flux quantization may provide a new understanding of, deeper understanding of fractional quantum Hall systems, of their anyons, and hence possibly of possible hardware for topological quantum computing. Thanks.